All right, I think we're good to go here, so let's get started. Earlier this week, we were starting our standard on volumes of solids of revolution, looking at different types of regions we could revolve around different axes of revolution. We started getting into what's called the disk method. Today in class, I'd like to talk about what's called the washer method, which is similar with one key difference where there are two different radiuses, because we have a gap between the region we're rotating and the axis of revolution. So for example, let me show you this GeoGebra link here before I get into our notes. All right, so while this is loading here, we can see we have two functions. In pink, the parabola f of x equals negative 0.1x squared plus 14. And in purple, the linear equation g of x equals 1/8 x plus 4. We're going to rotate this around the line y equals 0, or the x-axis. So when I do, I can see that as I rotate this, it kind of creates a washer or donut looking figure, because there is an interior radius, a gap between the linear function g of x and the axis of rotation, the x-axis. So when I rotate it completely, there's kind of a hole in the middle. And our goal here today is to use the washer method to find the volume of a region rotated about some given axis. So kind of some notes here. We're going to rotate some region about an axis of revolution. Notice that we have two r's, a capital R and a lowercase r. The capital R is the distance from the very top of the region to the axis of revolution. The lowercase r is typically the gap radius, the inner radius, the unshaded portion, the distance from the bottom of the region to the axis of revolution. And as we saw in that GeoGebra link, when I rotate that, it creates, kind of a donut or a washer. So our disk method formula from Monday was pi times the definite integral from a to b of r of x squared dx. I rotate this region, it creates a cylinder. The volume of a cylinder is pi r squared, and then the definite integral sums the volumes of each of the inner cylinders to make up our region. Now we have two radiuses, the capital R and lowercase r. The only difference here between these two formulas is this extra gap radius I now have to account for because of the inner unshaded region I want to exclude from the overall volume. Washer method is very similar. There's just two radiuses, top minus bottom. All right, so a couple examples I wanted to look at. So first up, find the volume of the solid generated by revolving the region bounded by the graphs of f of x equals x squared and g of x equals the square root of x about the x-axis. All right, so let's just take a look at what this would look like on Desmos. These are pretty basic functions, so I'm sure most of us already know what they look like. All right, so I can see the region outlined right here that we're going to rotate around the x-axis down below. This will be a washer method question because there is some gap region between the region we're rotating and the axis of revolution. That gap is the region we want to exclude in the overall volume using the washer method. All right, so we have f of x equals x squared. G of x equals the square root of x. Now we have a washer method scenario, so let's identify what the large and small radiuses are. The large radius is the distance from the top of the region down to the axis of revolution, and we are rotating around the x-axis, so I will kind of draw that in as best I can over there. The inner radius is the gap region. And we're rotating kind of this rectangular region about our figure, about the x-axis. So for our definite integral, we'll do pi times the definite integral from 0 to 1 of the large radius, which in our case is going to be the square root of x, squared, minus the inner radius being the gap region I do not want to include anymore, which is x squared squared dx. Let me stop here. Questions before I go any further? Okay, if there's nothing, let's keep going. Let's simplify before I find the antiderivative. X minus x to the fourth dx. The antiderivative would be x squared over 2 minus x to the fifth over 5 to evaluate between 0 and 1 and bring down the pi. Using fundamental theorem, it's not necessary to plug in 0, so all we'll do is plug in 1. Pi times 1/2 minus 1/5 which would be pi times 5/10 minus 2/10, or 3/10 times pi, 3 pi over 10. Of course, we can check this on Desmos. The integral from 0 to 1 of the square root of x squared minus x squared squared. Almost forgot to enclose this. Dx. 0.3 or 3/10 for a total volume of 3 pi over 10. Questions on any of these? All right, that's a pretty basic question. Let's look at one on the next page that kind of kicks it up a notch. What makes a lot of these volumes of solids of revolution questions difficult is because sometimes you're not always rotating around the x or y axis. Sometimes you have different lines of rotation. Arbitrary lines like y equals 8 and x equals 2. Sometimes it's best to use disk, sometimes it's best to use washer. You might not be given that information, you have to figure it out for yourself. So let's keep this region bounded by y equals the square root of x, y equals 0, and x equals 3, and find the volume as I rotate it around each of these unique lines below. We can choose to use either disk or washer based off of what we're trying to do. So y equals the square root of x. We also had y equals 0 and x equals 3. All right, so here is our kind of region. And first up, we're going to rotate it around the x-axis. When x equals 3, y equals the square root of 3. I'm just going to write that down now. That'll kind of come into play later. So first up, for the x-axis, would we choose to use disk or washer? What we're trying to do is take this rectangle and rotate it around the x-axis.
Would you use the disk method since there's no gap?
Absolutely. You would use the disk method. There is only one radius. And what is that radius? Well, it's got to be the square root of x. Good. Look for the gap. If there is a gap, washer. If there isn't, disk. Easy. Since I have a horizontal axis of revolution, this is going to be a dx integral from 0 to 3 of our radius, the square root of x, squared dx. So pi times the definite integral from 0 to 3 of x dx, or pi times x squared over 2, evaluated between 0 and 3. 3 squared is 9. I don't need to plug in 0, so wouldn't it just be 9 pi over 2? We could always double check that. From 0 to 3 of the square root of x squared dx. 4.5 or 9 halves 9 pi over 2. Now let's look at the y-axis. As with everything, my best help when I'm first starting these types of questions is to draw a picture. Even if you graph it on Desmos, I would still draw a picture. Because it really helps you put it in perspective. by drawing it yourself. As crude as my drawings might be. Okay, take a guess here. Disc or washer?
You would use the washer because there's a gap.
There is a gap. That gap is right here. We're trying to rotate this region around the y-axis. Would it be dx or dy? I believe it would be in terms of y. The depth of this region is some distance on the y-axis. The height of our cylinder is in terms of some y value, some length along the y-axis. So we'll do a dy integral. What are the two radiuses? Well, the large one is obviously 3. But what is the small radius? The gap. This distance is the square root of x. From the top down, from the top of the region down to the bottom. But what about the distance from the region over to the y-axis, to the left? We would need to solve this equation for y. I'm sorry, we need to put it in terms of y and solve it for x. So to solve for x, if y equals the square root of x, that means that x equals y squared. If this distance is y equals the square root of x, this distance is x equals y squared, solving for the other variable. So our definite integral is pi. We're not going from 0 to 3, we're going from 0 to the square root of 3. We're doing it along the y-axis of 3 squared minus y squared dy. Let me stop here for a minute. Questions if you got them. Okay, excellent. Let's keep going. I'll simplify this as pi times the definite integral from 0 to the square root of 3 of 9 minus y to the 4th dy. So 9y minus y to the 5th over 5 between 0 and the square root of 3. Don't forget to bring along the pi. All right. I always like when I have 0 as the lower bound because it kind of eliminates half the work. So let's just plug in the square root of 3. Well, what is the square root of 3 to the 5th? The square root of 3 to the 5th would be the square root of 3 times the square root of 3 times the square root of 3, basically 5 times. Square root of 3 times the square root of 3 is 3. Square root of 3 times the square root of 3 is another 3. Together, those make 9. So wouldn't that just be 9 square root of 3 again? Finding a common denominator. 45 square root of 3 over 5 minus 9 square root of 3 over 5 for a total volume of 36 pi square roots of 3 over 5. from 0 to the square root of 3 of 3 squared minus y squared dy. Gives us that funky looking decimal. Hopefully it's the same thing as 36 square root of 3 over 5. And it looks like it. All right, we did an x-axis, we did a y-axis. Try an arbitrary line like y equals 8. Since y equals 8 is another horizontal line, kind of like the x-axis we did here, I know right away that this is going to be a dx integral. For disk washer method, horizontal axes of rotation are in terms of x, vertical axes of rotation are in terms of y. So it was y equals 8. Yep, got it. I'm going to put 8 up here as the region that we are rotating, or the line that we're rotating this region around. Disk or washer?
Washer.
Washer indeed. We have 2 radii. Here's our representative disk from top to bottom. Large radius is 8. Now, what would this gap radius be? This is the square root of x. This is 8. But what's this? I believe it would be 8 minus the square root of x. Was that what we were going to say there? I'm sorry to cut you off.
Yeah, I was gonna say that, but that's good.
Glad you got it. Excellent. Okay. Let's do it. We'll go pi times the definite integral from 0 to 3 of 8 squared minus 8 minus the square root of x squared dx. Simplifying this as pi times the definite integral from 0 to 3 of 64 minus, well, let's see here. If I expand that, let me just write this out so I know I'm good. 8 minus the square root of x times 8 minus the square root of x. And I expand that, it would make 64 minus 16 square roots of x. Negative root x times negative root x is positive x dx. These essentially cancel out, but I'm left with positive 16 square root of x minus x. All right, so let's find the antiderivative of this. 16 squared of x. I think that's x to the 3 halves. So 32 thirds. Yep. Minus x squared over 2 to evaluate between 0 and 3. Don't forget to bring down the pi. Pi times 32 thirds times 3 to the 3 halves minus 9 halves. Three to the 3 halves. That's the square root of 3 to the third. So that's the square root of 3 times the square root of 3 times the square root of 3. Which would be 3 square root of 3. So pi times 32 thirds times 3 square root of 3 minus 9 halves. These cancel out. Pi, let's see, that's 32 square root of 3, but I'll find a common denominator. 64 square root of 3 over 2 minus 9 halves. So all together, I'll put pi times 64 square root of 3 minus 9 all over 2. Not the best looking answer, but I think that's as simplified as we can make it. Of course, we could always check on Desmos. From 0 to 3 of 8 squared minus 8 minus the square root of x squared dx. That awful looking decimal. Hopefully this works out to be 64 square root of 3 minus 9 all over 2. Yep, looks good. Of course, you could always put the pi in here. I don't know why I don't. I just don't. It would be the same. Questions, ladies? Okay. Would you guys like to try the last one on your own? Tell you what, though, I'm going to change this to be x equals 3, though. As you guys are getting started, dx or dy? Is our integral in terms of x or y?
Would it be in terms of y?
It would be, because we're running along a horizontal axis of revolution. So I know it's in terms of y. If you see that rectangle I drew, it's running horizontally. So its depth or height is some distance along the y-axis. How about disk or washer, now that I know it's in terms of y?
Disk, because there'd be no gap if
There'd be
it's...
no gap. So there's only one radius. What is this radius? Keep in mind that this is y squared. Y squared is this piece. I need this piece.
Would it be 3 minus y squared?
You got it.
Okay.
Very good. So pi, we have to change our bounds from 0 to the square root of 3 of quantity 3 minus y squared dy. All right, I think we're good to go on the setup, so let's just start simplifying. Pi times the definite integral from 0 to the square root of 3. If I expand that, it would be 9 minus 6y squared plus y to the 4th dy. So let's see here. Is that 9y minus 2y cubed plus y to the 5th over 5 between 0 and root 3? Don't forget the pi. So plugging in root 3, I don't need to worry about the 0, would give me pi times 9 radical 3 minus 2 times root 3 to the 3rd. That's root 3 times root 3 times root 3. So that's a 3 with an extra square root of 3. Plus, that's root 3 to the 5th. So that's 4 root 3's. 3 times 3, or 9 root 3 over 5. Put this in terms of a common denominator of 45 square root of 3 over 5 minus, that's 6 square root of 3, which would be 30 square root of 3 over 5 plus 9 square roots of 3 over 5. 45 minus 30 is 15. 15 plus 9 makes 24 pi square roots of 3 all divided by 5. Free to check out on Desmos, but that should be right. Like I said, draw a picture, draw a picture, draw a picture. We use the same region for each of these last 4 problems, changing up the axis of revolution, and it completely changes the setup and procedure. Do you do dx or dy? Do you do disk or you do washer? That's really hard to unpack without drawing a picture first.
Will you go over when do you know when to use dy versus dx?
So, but next week, good question. Next week, it's going to change because we're going to introduce a new method called the shell method, and it's going to be different. When I'm doing a horizontal, I'm sorry, let's just start with vertical since that's what I have here. So when I'm doing a vertical axis of revolution, my representative disk is going to run perpendicular to that, which means it's going to lie flat, and we need to use a dy integral. For vertical axis revolution, use dy. Use it in terms of y. For a horizontal axis of revolution, like when we rotated around the line y equals 8, our representative disk runs perpendicular to that, so you can kind of see it standing up. And its depth or height is some distance along the x-axis, so we need to use a dx integral in terms of x. Does that help?
Yes.
Okay. That's going to change next week, so for now, we'll leave it there. Anything else, ladies?
No.
Okay. Well, I would for sure maybe start trying some of these practice problems in Standard 23. Next week, we're going to cover the shell method and quiz a week from tomorrow on Standard 23. Disk washer shell method, volumes of solids of revolution. Okay?
Perfect.
All right. Anything else, you just give me a shout. I'd be happy to hop on a call here if you have any questions, all right? When you're doing some practice. Yeah, have a good day.
All right, you too.
See you guys.